Hi, my name is Wenxing Ding, and I'm presenting on the privacy utility trade-off in peer-reviewed data analysis. This is joint work with Professor Nihar Shah and Professor Wei Nawal. A fair and efficient peer review process is of utmost importance to the development of scientific research. There are, however, a large number of challenges in peer review pertaining to its fairness and efficiency. The research on improving peer review suffers from a considerable handicap: unavailability of data. Concealing the identities of reviewers from authors of any paper is paramount in most peer review systems. Thus, releasing any peer review data is fraught with the risk of compromising on its privacy. There has been much research in the field of privacy. There's also much work in the area of peer review. However, there's little overlap in these two fields, and many researchers cannot release their research data on peer review process due to privacy concern. Therefore, our goal in this research is to release some peer review data while concealing the reviewer identities for each paper. There have been many techniques in releasing perturbed data. However, this perturbation can considerably hamper the utility of the released data. So our question is, how can we considerably improve utility while ensuring the same level of privacy? First, I will introduce the problem setting. In a peer review process, there is some private data that's usually known to the conference organizer. Private data can be viewed as a complete bipartite graph. The score associated with each review is known. Moreover, reviewers do not maintain anonymity. Such data is never released to the public. There's also some data for a peer review process that is released to the public. In public data, however, reviewers remain anonymous to the authors. The known information are, for example, identities of papers, identities of reviewers, number of paper each reviewer reviews, and number of reviews each paper receives. The review scores to the papers are known information as well, but crucially, the reviewers are anonymous from the authors of the papers. One canonical example of the framework is to release a sorted vector of mean scores given by the reviewers. Note that this is a general framework, which can also be used to release other properties, such as miscalibration or subjectivity. We measure accuracy using the mean squared error between the output and the true vectors. In addition, this framework is applicable to any privacy paradigm that perturbs the data, including the commonly used differential privacy. First, we made some key observations on this problem setting. Note that we use noisy data to refer to the data perturbed by the privacy paradigm. First, we observed that projecting the noisy data onto any convex set containing all possible values of the true data will compromise neither privacy nor accuracy. Secondly, we note that projection on a quote-unquote smaller convex set is desirable for higher utility. And lastly, there is a non-trivial amount of peer-reviewed data available publicly, and we should use it to achieve high accuracy. Given the observation, the first thought was to project the noisy data onto the set of all possible true values. However, we proved that doing so can actually increase the error. And since we would like to project the noisy data onto a quote-unquote small convex set, it is natural to consider the convex hull of all true values, because the convex hull of all true values is the smallest convex set that contains all true values. However, we prove that projecting on the convex hull of all possible true values is NP hard. This implies that projecting onto the convex hull is not time efficient, and therefore we look to project onto a convex set containing all true values. We would like to design a polytime algorithm that projects the noisy data onto a quote-unquote small convex set. You may want to ask, what is a quote-unquote small convex set? Intuitively, if the underlying review scores have very nice structure, then our output should have very high accuracy. Thus, we come up with 3 axiomatic properties to evaluate the convex sets. The first axiomatic property states that when all review scores are identical, then we should return a vector with all of its entries identical to that score. This is a true vector, and this can be obtained from the public data only. Secondly, when every reviewer reviews just one paper, then we should be able to return the sorted vector of the scores. This is, again, the true vector and can be obtained from the public data. Lastly, when we consider a scenario when all but one papers receive all 0 scores, the output vector should also be able to equal to the exact answer, and this can be obtained from the public data. Therefore, we design an algorithm that has 2 steps. In step 1, we will compute some lower and upper bounds for each entry of the true data. In step 2, we'll project noisy data onto the convex set enclosed by the bounds. We're using an example to demonstrate how we compute the bounds. In this example, we have 3 papers and 3 reviewers. Each paper is reviewed by 2 reviewers, and each reviewer reviews 2 papers. First of all, we will list all tuples consisting of scores from distinct papers, and we will sort the tuples by their means. The subscript here just meaning the paper that each score is associated with. Then we were having the tuples as the vertices, and we're drawing an edge between 2 tuples if their entries do not overlap. We define the length of the longest left and right chain for each tuple. Then we use 2 criteria to decide if the mean of a tuple could be the lower bound of the ith entry in the true vector. So our algorithm will output lower bound 0, 1, 2 for the example on the right. And computation for upper bounds is very similar to the computation for lower bounds. And our algorithm will also output upper bounds 0, 1, 2, which will give us an exact answer of 0, 1, 2 for this scenario. And that also matches our third axiomatic property. And then we will do a projection, which is a simple L2 projection with 2 constraints. The first constraint is constraining the sum of the output, and the second constraint is constraining the output to be sorted. We did synthetic simulations to show that our algorithm greatly improves the utility of the released data. Here, the baseline projection is where we do projection with the 2 constraints, but we do not compute the bounds. In summary, We noticed that a fair and efficient peer review process is very important, but research on this field suffers from lack of data. We noticed that much peer review data cannot be released due to privacy concern, so we want to release some peer review data while ensuring reviewers' privacy. We noticed that privacy techniques will reduce the accuracy of the released data, but we can use public data to improve accuracy. We showed that projection onto the set of all true values can harm accuracy, and projection onto convex hull is NP-hard. So we designed an efficient algorithm to project noisy data onto a quote-unquote small convex set. Thank you.